Okay, so the real number system. The real number system is every number that we use for regular use. Okay? All the numbers that you can think of are real numbers. Why do we specify the word real? Because there is also a whole set of numbers called imaginary numbers that you do not need to worry about. Okay? That's why the real is there. And those imaginary numbers, we'll talk about them just a little bit later on this page, but you don't really need to worry about them. We'll begin with, and these are words you need to know. We will begin with natural numbers. Now, right now, this is going to seem useless, right? Because they're just numbers. Why do they all need names? But as you go further in math, you'll find there are situations where each of these categories comes into play. All right? And by the time we're done this page, I'll give you a couple of examples of that. All right? So we'll start with the first one. Natural numbers. I like to call the natural numbers the counting numbers. What do I mean by that? Well, if you were back in kindergarten with Mrs. Bad Crumble and she put a whole bunch of things on your desk and said, let's count these, boys and girls, you would all go 1, 2, 3, right? Until we got to the end of the pile of stuff. What number did you start counting with? 1. Is 1 really the first number? No, but we would all call it 1, right? Because we don't like the number 0. It gets in our way. When we have babies, we don't say that they're 0. Even after their first birthday, we still count them by months. A lot of people count their babies by months for a long time past the first birthday as well. I don't really get that. I'm 43, so I'm 12 times 40, 480 and 36. I'm 516 months old. I don't get it. You know, I've had 2 babies. I stopped counting at months once they turned 2. But there are people, oh, he's 34 months old, so your baby's almost 3. Just say that. But whatever. Counting numbers. They are, again, 1, 2, 3. How far can we count? Can we ever get to infinity? No. So we can't really count to infinity, but that is where the numbers end, right? Infinity is a concept. It's not an actual number. So 1, 2, 3, on and on and on, up to infinity. Everybody cool? All right. So that is technically the smallest group because it's only 1 up to infinity. Everybody okay? All right. I know it's stupid to say something that goes to infinity is small, but trust me when I say that, okay? The next one, whole numbers. Whole numbers are the naturals plus 0. So 0, 1, 2, 3, up to infinity. So see, it's slightly bigger. 1 number bigger. Everybody good? Okay. And thirdly, the integers. These guys are the wholes plus negatives. So negative infinity, -1, -2, 0, 1, 2, positive infinity. Is everybody cool? If you're a natural number, you're automatically a whole, you're automatically an integer. But it doesn't work the other way. You can be an integer without being a whole and without being a natural. Everybody good? What is missing from these 3 examples? What numbers are missing? Decimals. Well, no. 4, 5, 6, 7 are where the dots are, dude. Decimals, right? And what are decimals really? Smaller parts of a number. But how do we get a decimal? What does it start as? A fraction. Okay? So the next bunch are the rational numbers. Now we are going to use that word a bazillion gajillion times. A rational number is anything that you can express, so write, as x over y, but there's some rules. X and y have to be integers, and y can't equal 0. Okay? So it doesn't matter how crazy the fraction looks. If it is an integer over an integer, it's a rational number. Is everybody cool with that? So even if I gave you a fraction like this, 10,311 over 32,741, that's still a rational number. Even though if we were to punch that into our calculator, we would get a hideous decimal. Is everybody cool? That's the fraction side of things. But as Michael said, there's another side of this, right? The decimal side. And the decimals, because every fraction can become a decimal, if you're a rational number decimal, then you have to do one of two things. One, you have to end. So, for example, 0.537. The decimal ended, so it's rational. Everybody cool with that? Sooner or later, the 7 will show up. Why is that a rational number? Because that is really 537 over 1,000. Everybody should know that from like grade 6, yeah? Okay. The other rule is if it repeats. What do I mean by repeats? What's 1 divided by 3? 3, 3, 3, 3, 3, 3, 3, 3, 3 forever, right? Now, is 1 divided by 3 a rational number? Is that an integer over an integer? 1's an integer because it's right there. 3's an integer because it would be right there. So 1/3 is a rational number, yes? But that decimal will never end. It will go 0.333333 forever. So 0.33 with one of those. Everybody remembers these, right? This notation. We're all good? So everybody's cool with natural, whole, integer, and rational, yes? All right. Now, being the intelligent group of people that you are, what then, if a rational number is a fraction, or a decimal that ends, or a decimal that repeats, what then must an irrational number be? A decimal that doesn't end. What's the most famous one? Pi. So irrational numbers are decimals that neither end nor repeat. Now, why, for irrational numbers, is it only decimals? But for rational numbers, there's 2 parts to the definition. Because a fraction is automatically a rational number. So it can only be a decimal down here. And as Aiden just said, pi is a famous one. Does anybody know any others? Okay, that's cool. I didn't really expect you to know many others. There are a bunch that you're going to use, but for our purposes in grade 10... Oh, sorry, Michael. Tan, cosine, sine? Yeah. I know, but what is tan? I have no idea. Tan. Opposite over adjacent. Yeah, opposite over adjacent. Isn't that a fraction? Yeah. So isn't a fraction a rational number? It's multiplied by something. It just says tan. Okay. Tan equals O over A, yes? Yeah. Okay. There's theta. 7, 9. O over A is 7 over 9. Isn't that a fraction? So is it rational?
Yes, but I was just thinking like finding a group type of negative form. But that means that
There's a value. Oh, I understand. Where we're going with this should help with what you're saying right now. Okay? So, for our purposes, irrational numbers for us in this grade are these things. I want to erase all this tan stuff first. Are these things. What is the square root of 2? Use your calculator, because you don't know it. What happens? 1.414. Keep going.
2, 1, 3, 5, 6, 2.
And then your screen ends, yes? Is there a pattern there? Does it repeat? And your whole screen is filled up, yes? Okay. That is an irrational number. Always. A square root or a cube root that fills up your whole screen, for your guys' purposes, is an irrational number. So all the non-perfect roots are irrational. Is everybody with me? So root 3, is that irrational or rational? Irrational, because it's 1.737 blah, 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 right? Root 3 is irrational. What about root 4? What's the square root of 4? 2. So is the square root of 4 rational? Yes. Is everybody good? Okay. Everybody's happy? Now, there are some, what's the word I'm looking for? Not outliers, but there's some weird stuff with this that we're going to get to when we get to more in-depth into square roots. But for most purposes, this works. Now, let me ask you this. What do you think the square root of 1.44 will be? Rational or irrational? Why? Because when you actually do that, it is 0.12 and the decimal ends. So even though this looks like it will be irrational because it's a yucky number, it ends up being rational. Is everybody cool? Yeah? Okay. Oh yeah, 1.2. Not 0.12. 1.2. Everybody's good? All right, little bit of grade 3 work for you. Turn the page over to page 86. How do you convert something to a fraction? I'll give you a hint. The first one's already done for you on the first page, but I use 5.537. What do you do with that to turn it to a fraction? Oh, that's very complicated, but yes. Billy Bob. 12 over 100. Why? 0.12 is 12 hundredths. Yes? We remember place value with Mrs. Bad Crumble. Ones, tens, hundreds, tenths, hundredths, thousandths, 10,000ths. That's why I got a bigger table here, because when I say it makes spit, and I wanted you guys farther away. Now, would you leave it that way for Mrs. Bad Crumble? No, of course not. What would you do? You would make it 6 over 50. Would you leave it that way for Mrs. Bad Crumble? No, what would you make it? 3 over 25. Everybody's cool?
Yes, left alone, that would be
It would be okay in that it is a fraction.
it's still correct.
Yes, it is. It is a fraction. And it is a correct fraction. And I, unlike Mrs. Bad Crumble, who most likely would have marked that wrong, at least every Mrs. Bad Crumble I have dealt with would have marked that wrong. I am not those people. Now, who remembers how to deal with B, if anyone? What, does that little bar mean? It means it repeats. So this is really 0.11111 for how long? Ever and ever and ever and ever. So how can we convert that to a decimal? 1 over infinity? It's a good guess. 1 divided by infinity would be a really tiny number, though, wouldn't it? A lot tinier than that. Michael?
If you were to just do rounding for the last decimal, not last decimal, but the 2 places after the 0, so you should have 11 over 100.
So you want to say it's 11 over 100. That would be 0.11, and then it would end. So that loses all of those decimals. Right? I'm not saying you're right or wrong. I'm just saying that's what you think we should do. Does that make sense? It makes sense, sure. It's going to be close to 0.11, but it's not 0.11, is it? Because it's going to go on forever. So this, if there was no bar there, this would be 0.1, yes? And what would that be? Billy Bob is good at this. What would that be as a fraction without the bar?
10 over 100.
10 over 100 would work, but 1 over 10 is the simplified one, right? Everybody cool? But it isn't 1 over 10, is it? It's really 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 till I run out of breath, yes? So, which of these two is bigger? 0.1 or 0.111111111111111? Which is bigger? 0.11111 is bigger, isn't it? Right? Which means that 0.111's fraction must be bigger than 1/9. I just gave it away. Strike that, reverse it, edit. 0.11111's fraction must be slightly bigger than 1/10, yes? And to be a fraction, it must be an integer over an integer, yes? So we know the 1 can't change, so I must need to change the denominator. What is the denominator that is closest to 10, that is an integer, and is slightly bigger? 9. What? 9 is smaller than 10. But it's fractions, isn't it? If I cut a pizza into 10 slices, which is a hard amount of slices to cut a pizza into.
I'm hungry.
A tenth, if I cut a pizza into 10 slices, and we all get a slice each, 10 of us, and then I cut a second pizza into 9 slices, which slices are bigger? The 9s. Everybody understand? So, this says that, all right, I recognize it's got to be a fraction. I recognize it's got to be an integer. I recognize it's got to be a little bit bigger than 1/10. So the only integer that's bigger than the next bigger integer than 1/10 is 1/9. Everybody good? Now, Aiden.
So basically when the decimal repeats, just reduce the denominator by 1.
You're giving me away. But yeah. What does this tell us? When this decimal repeated, instead of doing 1 over 10, we did 1 over 9. Everybody good? So what do you think happens here? This is very slightly different than the bar. What do those dots mean? It means that it continues. And what is the assumption that we are making here? That the 2's go on forever, but we don't know. Everybody cool? So the assumption here is that this is 0.2 repeating, right? Now, if there was no bar there, this would be 2 over 10, yes? But it can't be 2 over 10. What must it be? 2 over 9. Everybody cool? A repeating decimal, we're going to put it over 9. Now, look at D.
Oh, love that.
What's different? Only one number is repeating. So, if it was 54 repeating, what would it be? 54 over 99, right? So 54 repeating would be 54 over 99. Easy peasy lemon squeezy, right? But we don't have that, do we? What do we have? What do we only have the 4 repeating, yes? Now what do we know about a repeating decimal? If there's a repeating decimal, we know we got to have a 9 on the bottom, correct? So we know that we're going to have a 9 down there. Agreed? Now, does that decimal repeat? No. So there's 0 other repeating decimals, yes? Do I have a number that represents nothing? There's no number that represents nothing? 0. So I got 1 repeating and then I got a 0. That makes sense, right? I got 1 repeater, the 9, and then I got no other repeaters. Everybody okay? Now, the problem now is what goes up top. What are some options? What could we write in the numerator? .111 we put a 1. .222 we put a 2. .12 we put a 12. What would be a good guess to put here? 54. Well, let's see what happens if we do 54 divided by 90. It's not .544444, is it? So that's wrong. That can't be it, can it? So, what are some other options? 49? Why do you think 49? 49 is correct, but why do you think so? The answer is indeed 49 over 90. And if you go to your calculator, 49 divided by 90, there it is. Why?
Is it because the 4 is repeating on the original number and you have the 9? So you just do that. I don't know, that makes no sense to me too.
Why is it 49? Who can see any kind of relationship between 54, those two numbers, 5, 4, 54, and 49?
Subtract the non-repeating number.
Subtract the non-repeating number. And that gives it to you. So that is 54, what we had, but I subtracted out the non-repeater. Why? Why does that make sense? We got rid of it, right? We didn't count it down here. And this will work all the time. Everybody cool? Okay. Next, we need to do some work here. Most of this you can do in your head. You've seen that once this year. You're going to see it a lot more in a little bit. But using what you know right now, give all of these A through G, I think it only goes to G, A through G, a category. Remember, if they're natural, they already fit into whole, rational, and integer. So you only need to put the smallest group. And just to remind you, it goes like this. Naturals, then wholes, then integers, then rationals. And of course, there's irrational on the other side. So you choose, remember, you only need the smallest one. So if I gave you, for example, number 7, where would that go here? Where would the number 7 go? It would be in natural, which means it's automatically in all the other ones. Everybody with me? You don't got to write all the letters. So, cube root of 14. What's a square root? The same number multiplied together, yes? So a cube root is the same number multiplied how many times? 3 times. Is there a number that you can multiply by itself 3 times to make 14? 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Did we hit negative 14? So what is that? Irrational. Everybody see what you're doing? Go. A through G. Put your best guess, because there's a couple of tricky ones in here. Talk to your neighbor if you need to. This is not a test. Because once we're done this, you're working on work. Yes. Yes, Billy Bob. It is still class. You have to do some math at some point in math class. Well, you don't have to. I mean, it's the Canadian school system. We'll just move you along anyway. Okay.
That's impossible. No.
All right. So, what is B? It is rational, but does it get any smaller? Is it an integer? It is, right? Is it a whole number? Yep. Is it a natural number? Why? What is the square root of 25? 5. Do we hit 5 when we start counting? 1, 2, 3, 4, 5. Yeah. So it's natural, which means it's automatically everything else. Everybody with me? So it is rational. I'm just going to write all of them. It is an integer. It is whole. And it is natural. Natural is all you need as long as you recognize that they all fit in natural. Everybody cool? Okay. What about that one? Why is it rational, Zaro? It's a giant decimal and it doesn't repeat. But it ends. So this is rational. Is it anything else from our list? No. If I were to make that a fraction, it would be 5 and 319,754 1/millionths, which is a crazy number. It's there for math. What about D? We've just done exponents. Negative 2 to the 4th power. Is the negative part of the base?
It's a natural.
It is a natural, because what is it?
Because when we do it, we find 16.
We get 16, and 16 is natural. Right?
Oh, it's the sum, not the sum.
What about 9? Natural. What about F?
It's impossible.
Why is it impossible?
Because 4 squared is 2. If you had
2 squared is 4, you mean?
2 squared is 4, yeah, but the square root of 4 is 2. The
Right.
issue is that if you have 2 times 2 and they're both negative, you end up with a positive 4. To get a negative 4 would be impossible.
So this is impossible, isn't it? This can't exist, can it? This is an imaginary number. And the reason those exist is because when you get up to really high-level math, Sometimes you can't get rid of the negatives. So the imaginary numbers were kind of invented for that. But you don't need to worry about it. For your guys' purposes, all the way to pre-calc 12, if this happens anywhere in your work, the work is done. It can't be finished. Everyone cool? Okay. And what about that one? Why? 1, 8, 1, 8, 1, 8. Wait. If this is there, is it rational? Forget the dots. If that is there, is it rational? Guaranteed, locked in, yes? But we have those dots. So here, what is the best thing we can do? We make an assumption. What is our assumption? What does this look like? It looks like the 1, 8 is repeating and going to continue repeating. So we are going to assume that this is rational. Is everybody with me? Why can we not guarantee it? What if the 27,000th decimal place is a 4? Then it would be not rational. Does everybody understand? Okay? So sometimes the best we can do is an assumption. Everybody cool? All right. I am shutting up. You have 33 minutes to do this little page. Page 87. 33 minutes. And you have 4 grown-ups in the room. Should anyone have homework? No, I lie. You have 23 minutes because we want to go over the test. So I'm going to set a timer. And we'll go over the test. Then, go do your P's and whatever you need. Please do. And I'm doubly lying because for the first couple of moments you only have 3 grown-ups because I have to enter the last 3 tests that I marked into check my progress. How are you, Kelvin? You got big...